All right, so to start with graphing, we're going to start just kind of understanding where these min and max points take place. So 4.1 is literally called the maximum and the minima. Maxima and minima. That does not, oh, minima. No, minima. That's why that didn't look right. That should be an I, right? Maximum. So maxima and minima, we kind of put them under an umbrella term called critical points. They are certainly critical points on a graph because if you know where a max and a min is, you can help form your graph, right? So these are our critical points. And if you have any crazy function, you know, a couple things we're going to go over when you look at a function. So this is just some crazy function. Clearly, what happens, let's talk about maximums here. You get an idea, a maximum is going to occur right there, right? That would be a maximum point. And then you have this point here. All right, so we'll call this point A and that point B. So point B is clearly more maximum than point A, right? In fact, point B, and we'll get to all the terminology and I'll write them all out. We have what we call local maximum and minimum points, and then what we call them local or relative, and then what we call absolute maximum and minimum points. So when we're talking about absolute, we're talking about the absolute highest point on that graph. So that would be B, right? When you look at point B, you say, yep, that is what we're going to call, oh, sorry, let me turn my email off or it's going to keep coming up. Let me just do that real quick. There we go. Okay, that's definitely an absolute maximum. But point A is important too. So that's what we would call either a local or a relative maximum. So does that make sense? And I want you to understand it conceptually first before I give you the definitions, because when you read the definitions, they can get a little confusing. All right? So a local or relative maximum would occur as long as it's higher than all the points directly around it, right? Where an absolute maximum occurs when it's higher than every point in the domain, right? The other thing I want you to notice is when we talk about the absolute max and min, we're actually talking about the y value of the graph. So let's suppose this function, I'll go ahead and put an axis around it, right? So this function has an x value, is at a point xy, right? As any point on a graph is at a point xy. You would say it has an absolute max of y, whatever y is, at x. So if y is 10, the absolute maximum value of the graph is 10. It's just the y value. But it's at x equals whatever, 3 or something like that. So just to kind of give you an idea. Same would occur with local. Okay? Same idea with local. Now, when you look at this particular function I put up here, do you see an absolute minimum? Do you see an absolute minimum? Correct. That it would be a no. Do you see a local or relative minimum? All right. Do you see the difference now? Yeah, we have, hey, this would be a local min, right? But there's no absolute minimum because these graphs will go down into infinity if we're talking about the entire function. Okay. So again, just giving you some conceptual stuff first before we go into the details of all the definitions. The other thing that can change how we look at the minimums and maximums is we can restrict the domain. Right now, we're looking at the entire function. That means we're looking at the domain negative infinity to infinity, right? What if I changed it to a closed interval? And I said, all right, I now only want to look at I'm making numbers up, obviously, to if I restrict my domain to -4 to 8 and no longer go from negative infinity to infinity, does that change any of my max or mins? All right, so let's talk about the maxes first. Well, we still have an absolute max, right? At x, I can see it there. That's still an absolute max. Do we have any other local max than if I restrict that domain? No, because the other one's outside. Because I'm only going to look now between -4 and 8. So restricting it from -4 to 8, we still have our same absolute max, right? Here's my question. I still have a local min where I had a local min before, right? Still a local minimum. By restricting that domain, do I now have a absolute minimum? What do you think? Do I now have an absolute minimum of that graph? So we're forgetting everything over here, and we're forgetting everything over here. We're just going from here to here. Do I have an absolute minimum value? Yes. Since we're on the closed interval, I now have an absolute minimum value. This is definitely lower, right there. Do you see that? The reason I want to show this is to point out as we go through the definitions, it's important to know the domain you're working on when you're talking about absolute min and max. Is it an open domain, negative infinity to infinity? Is it a closed domain? If it's a closed domain, those endpoints matter and need to be taken into consideration. Okay? So that is my kind of crazy conceptual idea of our mins and maxes. Absolute mins and maxes. Together, mins and maxes are also called extrema because they're extreme values on your graph. All right, so now I got to get into those formal definitions, but hopefully those formal definitions will make sense to you. So the first formal definition I want to give you, I am going to move this up a little so I have some room. I want a definition. I don't want red. And a lot of this stuff today is very heavy with definitions and theorems, just so you're aware. And then Tuesday's class is more application of everything, okay? So the first definition is that of the absolute max and min. And hopefully after everything I did, you see why each little piece is kind of important. All right, so we're going to let f, which is our function, let f be defined on a set D. Whoa, I don't know what happened there. Oh, let me do this real quick. That might help. So when you see things like on a set D, think of that as the domain, right? Whatever that domain is. It could be open from negative infinity to infinity. It could be a closed interval, like our -4 to 8. And let f be defined on a set D containing a point C. All right. So if f of C is greater than f of x for every x in D, then f of C, because remember, when you put the f of C, that means the y value, f of C is the absolute maximum. Okay, and then obviously the other way around, right? Same idea. If f of C is less than f of x, for every x in D, then f of C is your absolute minimum. And I do shorten these. So one of the things I strongly suggest after going through this lesson today is look through those PowerPoint slides. Make sure you read them and understand them, everything that's written in them. And then, of course, the other term, an absolute extrema value is either an absolute min or absolute max. So if you are asked to find the absolute extrema, that means both max and min. And I want to do an example of one that shows why domain matters. So let's look at a nice simple one to look at why domain matters. And also keep in mind, you don't want to write all this down right now. This is in the PowerPoint slides. Okay, remember, I summarize the PowerPoint slides when I do the lessons. So all you got to do is go online and it's all right there if you miss any of it. So let's take a look at an example. Because the important thing is to note the interval matters. So here's your example. Let's do a basic graph. Y equals 4 minus x squared. All right. We should be pretty familiar with this graph on its own. And let's start with the full domain on, remember, it's on D, D meaning the domain, and we're going to go fully from negative infinity to infinity. We'll start there. Okay, first of all, it's an x squared graph. What kind of graph is it? Parabola, and it's opening where? Down, but it's moved where? Up 4. So we know how to graph it, right? Yeah, clearly on Tuesday, we're going to be doing like x to the 4th graphs and stuff like that, because you all know the x to the square graphs and how to graph those. So this is my 4, and boom. And just to make sure we're good, can you tell me what these points are? Let's get the x value for those points. Where's it crossing? Where is that graph going to cross the x-axis? At which 2 values? 2 and negative 2. All right, so there's all the points we need. All right, so if we're on the full domain of negative infinity to infinity, what type of extrema? And I'm talking about mins, maxes, locals, absolutes, whatever. Mostly absolutes. Do we have any absolute extrema on this one? What do we have? Yeah, we have. Now let's make sure when you're stating it, we state it correctly. We have an absolute max of what value? 4. The absolute max or min, the value is actually the y at, this is how we state it, at x equaling 0. Okay, so that's how you're going to write it. Oh, easy. I've got an absolute max at x equals 0, of 4 at x equals 0. Okay, any mins? No. Right? No absolute min values. Okay, let's change the domain. Now I want you to sketch this graph on your paper, but now change the domain from same thing. Let's use brackets. We're going to change D to 0, 2. Closed. Okay, so this is also a good review of closed and open intervals. So clearly I'm only looking at half the graph, right? And because it is closed, I can put those, all right, it's kind of funny looking, but you get the idea, right? Does that make sense? Is that the right graph? Okay. What do we have? Absolute max? Yeah, it doesn't change. Max of 4 at x equaling 0. Do I have an absolute min now? Yeah. What is my absolute min value? Yep. 0 at x equaling 2, right? So again, this is just practice, making sure we learn how to use it. All right, you see where this is going. We're going to go through it quickly now. Let's change the domain again. And I think this is good because as we get into the graphing, you've got to use this interval notation for your domains and everything. So this is good practice. Let's change the domain to one little change. What did that just do to my graph? That is, my thing is going. There you go. What did that just do to my graph? Yeah, it created an open circle here, right? So I'm going to exaggerate it. Does that make sense? It's not squiggy, but does that make sense? Open circle, closed circle. Do I have an absolute max? So we've learned limits. This isn't a limit, it has to be an exact value. right? So do I have an absolute max? No, because theoretically you can continue to get closer and closer and closer and closer and closer forever, right? And never reach it. So there is no absolute max. And if you, again, slides have really pretty pictures of all this. So that's why I encourage you to look through those slides or have them open while I'm doing class. That's fine. It's just easier for me to write things out as I go through it. So no absolute max. How about a min? Are we good with a min? Yeah, we still have a min. And how do I write it? Of 0 at x equaling 2. So part of this is to get it ingrained in your head how to write absolute maxes and mins correctly. A lot of students want to give the xy coordinate. All right, so what do you think my last graph's going to be? Yeah, there's a lot of things I can do. I'm going to go ahead and just skip right to that. We're going to skip the other way around. You get the idea. I don't want to kill, do this to death. Of course, that causes what? Do I have any max or mins? Nope. Okay, so again, domain matters. Another thing. Let's talk about continuity for a minute. Does continuity matter? Because remember, the definition said it just the function has to be defined everywhere on the interval. So let's suppose I had a function that, I'm just going to draw this function, right? So remember these discontinuous functions where you go along, you go along, you go along, you get a hold, but you got to jump. So the function is actually defined on the interval. Let's just call this 1. We'll put some numbers in there. It is defined on that interval. And if I were to draw this, write this function, it would be, one of these things, right? It's a simple y equals x. It's just the y equals x line. If between 0 and 1, whoops, not equal to 1. And then y equals 0 when x equals 1. Okay, so do be careful. Do I have an absolute? I'm not going to write it out, but we'll just talk about it. Do I have an absolute max? Do not have an absolute max. Everybody see that? No absolute max. Let's talk about the absolute min, though. Okay, it's defined. You gotta remember, this is defined everywhere on our interval. Our interval is 0 to 1, right? Because that's the only place we have our graph. It is defined everywhere here. It's defined there. So we have a function. Do I have an absolute min? And we didn't talk about this yet, so this is a good example. So remember, when you talk about an absolute min or max, it's that y value. So we would say, do you think I have an absolute min? Everyone's shaking, yeah, I think, yeah. So we have an absolute min of what? What's the value? 0 at where? Definitely at x equals 1. Anywhere else? 1. And, all right. So your absolute min or max can occur at multiple places. All right, that's the other thing to remember. It's still one single value of 0, but it can occur multiple times. And you've got to list all those. Okay. So we've played around with different graphs. Let's take us to our first theorem. So we've had definitions. Now we're going to do the theorem. And this is called the extreme value theorem. We're going to call it EVT. So when you see EVT written on your lab, oh, it's just the extreme value theorem. This is kind of a, well, there's a lot of theorems I call the common sense theorems. This is one of them. You'll see in a minute. Like, why do we even need a theorem for this? But we do. All right. So a function that is continuous. So, you know, those functions weren't continuous, right? So we want to specify a function that is also continuous on a closed interval. Okay, so this has a couple things here for this to exist. It has to be a function. That's important. It's got to be continuous. And it has to be on a closed interval. All right. Has an absolute maximum and minimum value on that interval. So notice, we didn't have continuity. This was a closed interval. It is a function, but what didn't we have here? It's not continuous. Continuous means, yeah, as soon as I take my finger off, it's not continuous. So it didn't work here. So yeah, we have no absolute max. That's fine. The thing is, if you have a function, if it's continuous, and you have a closed interval, you are guaranteed one absolute max and one absolute min. Because you can't get to a point. Theoretically, between two numbers, there's infinitely many numbers. So there is no final value before you get to that open circle. Mm-hmm. And because it goes off into infinity, there's literally infinitely many numbers to get to that open circle. It's that Zeno's paradox that theoretically you can never leave the room you're in. Obviously, it doesn't work because we leave the room we're in. Because to leave the room you're in, you have to at least get to the halfway point. There's always a halfway point, right? I understand. It's a theoretical concept, but in reality, you're like, yeah, but it's right there. Okay. So as long as these things occur, you're always guaranteed an absolute max and an absolute min. Because at the worst case scenario, you've got your endpoints because it's a closed interval. Okay, you can use those. Now, I will say, if it's not closed, you could have absolute max or mins. All right. You could. So if you had an open interval, you could. It depends on the function. So take a look. If I had an open interval and my function, went like that, I got an absolute max, right? I don't have an absolute min. I guess if my function went, there it is. Open interval, right? I do have an absolute max and min. But if it's a closed interval, you're guaranteed an absolute max and min. That's the difference. Okay? So let's talk for a minute. And there's more, like you can, you should really read through the slides a little bit. There's a lot of more pictures and examples. We could like go on with this forever, but I think you're got this much. Let's move on to defining what a local means then. How do we define a local? Because remember, for an absolute, it has to be that f of c value has to be greater or less than every other f of x, right? But local's a little bit different. So let's define, things going funky on me today. All right, I just have to slow down. Sorry, I write too fast and my computer can't keep up with me. So this is local. Local max and min. Okay, let's suppose C is an interior point on some interval, doesn't matter. We'll just call it I. It's not necessarily, we're talking local here, so it doesn't have to be the whole domain. So we're not calling it D. Do you see that? It's just a little interval on which f is defined, but f has to be defined. So suppose C is an interior point on some interval I on which f is defined. So you've got the whole domain D, but there's some little interval where you got a C value, okay? If f of C is for all x and I, in that interval, then f of C, sorry, forgot my f, is a local max. Yes. Suppose C is an interior point on some interval I on which f is defined. Okay? And I wrote it this way so I don't have to rewrite the whole thing for it. I can do this. Right? And if f of C is less than all the values, ba-bum, 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 bum-bum, bum-bum. You get the idea, right? I don't need to rewrite all those words. Clearly, if it's less than everything in that interval, it's a min. If it's greater than everything in that interval, it's... So the only real difference when we talk about defining a local versus an absolute is the interval it's on. When we're talking about absolute, we're talking about the whole domain. We're talking about local, we're just talking about some little tiny interval around that value C. Okay, that's the big difference. So this is just kind of good to get for defining it. And then we also have the local extreme value theorem. So we'll follow up with the theorem, which is the local I told you, a lot of just notes and conceptual stuff today. So this is going to relate back to the entire chapter you just did. All right, and this is where it's going to connect. The other thing I want to point out before I write this, every absolute max and min, think about this, is also a local max or min, right? Does that make sense? Think about it. Because every extreme value, every absolute max and min, which is the highest, so let's talk about the absolute max for a minute, the highest value on your entire function on your domain, isn't it also a local max? But can I say it the other way around? No. Every local is not an absolute, but every absolute is also a local. Does that make sense? So when I talk about the local extreme value theorem, I'm talking about every possible maximum and even the absolute, okay? So here we go. Let's see if you can finish this one. Here's the theorem. If f, your function, has a local max or min at C, and I know you can finish this one, and the derivative at C actually exists, all right, let's stop there 1 minute. And the derivative actually exists. Can you think of a circumstance where there could be a local max or min, but the derivative doesn't exist? Yes. Think absolute value graph, right? The V graph. There's an absolute max or min, right? If you think of the letter V, we'll go this way. There will be an absolute min. But does the derivative exist at that value? Absolutely not. Okay, so number one, it can't be a sharp. It has to be a smooth curve, right? Can't be sharp anywhere. So if f has a local max or min at C and the derivative exists, f prime of C at derivative exists at C, then what can you tell me about that derivative? Don't look, if you're looking at the notes, don't answer. What can you tell me about that derivative? It has to what? What is a derivative? It's a slope. It's a slope of what? It's a slope of the tangent line. And if it's a max or min, what must that slope be? 0. That's it. That makes sense, right? You can, you know, if you got a graph, boom. Here's C. You do a simple graph, boom. Yeah, the derivative at C has to equal 0. This is what you're going to use eventually to find where those max and mins are in your problems to help you graph them. You're going to use the fact that, well, let me find out where the derivatives are equal to 0. And I'll go from there. Now, we're going to broaden this because there's local extreme max and mins, but we're going to broaden this category to something bigger. We're going to go back to those critical points for a minute. And we're going to define a critical point, because a critical point is more than just max and mins. Critical points are, well, they're critical to graphing your graph. Like, they're the points you need where your graph does something that you must know exactly what's happening at that point, right? It's either a max, a min, or something else. That's a critical point. So where do critical points occur? Any interior point C of the domain F of F at which F prime of C equals 0. Well, that one makes sense because we know what's happening when F prime of C equals 0. We got a max or a min, right? But, or critical points are broader than just max and mins. Something also happens when the F prime does not exist, fails to exist. This is called a critical point. What does that mean it fails to exist? Well, keep in mind, we're talking derivatives. Derivatives are slopes. We know horizontal slopes are 0. That makes sense. That gives us our max and mins. What kind of slopes don't exist? What kind? Yeah, vertical tangent lines. That actually gives us some information too. So when we talk about critical points, we're talking about our max and mins and any place where the derivative doesn't exist. And there's lots of different ways where the derivative doesn't exist or the derivative. So we'll go through some pictures. It's n interior point C. Yeah, just n is fine. So what does it mean F prime doesn't exist? There's a lot of different ways it doesn't exist. So let's look at some pics. Where doesn't it exist? So F prime of C does not exist. Here's one pic. These goofy graphs, right? A hole in your function. It's not continuous, but it didn't have to be continuous. Doesn't exist. That would be a pretty critical point to know about your graph, wouldn't it? That's a critical point. The sharp things, those cusp points where your graph goes like this and then like does something goofy like that, right? Here. So these are pictures of where it doesn't. Wouldn't that be important to know? You don't have a 0 slope there, but that would be important to know. You've got something else going on. That's a critical point. here's an interesting one. This goes back to the vertical. So if your function comes down and takes a sharp curve, all right, that's too sharp. Let's see if I can make that without being so sharp, right? Okay. You got a function that looks like this, all right? There's C. Well, it's not really C. This is where looking at the notes is really helpful because their picture's way better than mine. Let me draw it one more time. Okay. Do you see if I were to draw a tangent line at C, what kind of line do I have? I got a vertical line. The derivative's not going to exist there. This is, you know, you're not going to have a derivative. You try to find the derivative, you'll know the derivative doesn't exist. So this would be something, a function that has, when you take the derivative, you have like x minus 5, right? In the denominator. If you have an x minus 5 in the denominator, your derivative is not going to exist at 5. Okay, there's a lot of different things that could occur because of that, and this is one of them. All right? But again, it's a critical point because something different happens to your graph at that point. These are called inflection points. And inflection points are something we're going to work with on Tuesday to graph as well. This is all setting you up to work on Tuesday. The other thing is, we know if there's a max or min, wait, there's a theorem that says it. I'm going to rewrite it one more time in red. If, in my own words, there is a max or min at C, then f prime of C, right? Known fact. We go with that fact. If there's a max or min at C, f prime of C definitely equals 0. Everybody comfortable with that? Okay. So here's the other question. If f prime of C equals 0, does that mean there's definitely a max or min at C? So we're good with, hey, if there's a max or min, we know f prime of C equals 0. Can you think of a situation where f prime of C does indeed equal 0, but it's not a max or min? In other words, if f prime of C equals 0, can I guarantee it's a max or min? What does it look like? So that's what I want you to think about for a minute. Can you come up with, so when you get a question like this, you have to come up with some counter example, right? You got to come up with a situation where the tangent line is horizontal, because that's what f prime of C equals 0 means, but it's not a max or min. Okay, you're onto something. Can you sketch it? And I don't mean absolute, it could be local, it doesn't matter. Can you come up with? It's kind of on the board for you already. I'm going to really drive you crazy. It's there. It's still up there. It's on the screen. In other words, I want a horizontal tangent line. We know, oh yeah, horizontal tangent lines occur All right, it didn't touch, but you get the idea. At a max, right? They occur at a min. Can you come up with something else the graph is doing and still have a horizontal tangent line? This isn't over here. That's not helping you. Flip it. What if I had never seen a graph like that? X cubed graph? So you got to be careful. So the point of all this is to get you to understand all the possibilities that occur when you have either f prime of c equals 0 or f prime of c not existing. Yes, you can have on a graph a horizontal tangent line. F prime of z equals 0, that does not mean it's automatically a max or min. There are things you're going to do, we're going to do on Tuesday, all these tests, to know, is it a max or min? Is it a inflection point? They're called inflection points. They were both called inflection points. Okay? So just kind of keep that in mind. A lot of different things can occur. All right? All right, I'm going to make you do a little math because you're looking bored. So you're going to do a little math, right? Get your pencils out. I'm going to give you a function. And if you have your notes, just close them so you don't have the answers in front of you because I'm taking it from the notes. I'm going to give you a function. There's a function. Find for me we'll start with critical. Well, see if this function has any mins or maxes of any kind. How would you do that? Okay. So what do you think the first thing you're going to do is to try to find a max min? We're not going to just graph the function because that's like cheating, right? How can we use algebra or calculus without graphing? What do you think the first thing we got to try doing is? You just took a test on it. Yeah, you're going to take the derivative. So let's take the derivative. Let's find y prime. Oh, you can take the derivative. See, you thought you were going to forget all that. No. I told you we're going to be doing derivatives through this whole unit. Every day we're going to do derivatives. So I got x squared times ln x. So I'm going to use what? Product rule. How do you want to start it? Doesn't matter. Everyone starts it differently. I'm just going to start by writing x squared. How's that? Oh, what's the derivative of ln x? Plus, what comes next? I like making you do logs and stuff like that because it makes sure you have to remember how to do them, right? A little bit. Clean it up. Always clean things up because you're going to have to end up doing what with this? Setting it equal to 0. So you want to clean it up, get it as neat as possible. X squared over x is just so we're going to take that and we're going to set it equal to so we're going to say, okay, x plus 2x ln x equals 0. You are going to get comfortable solving equations like this. I promise. So let's think about this. What do you want to do? Because I know, you know what happens the second I put an ln x in there? You forget all your basic rules of solving equations. What's your instinct tell you? What do you, anybody want to try? What's an instinct tell you want to try doing? Problem is you got, if you factor an x out, you can't get x by itself, right? Because you still have the ln x. So you can't even get, x is already all on one side of an equation, right? So here's the thing. If I gave you the equation x squared plus 7x plus 12 equals 0, you would know exactly what to do, wouldn't you? If I gave you a trinomial, you would know to factor it. You would know to set each factor equal to 0. So you were on the, yes, you always want to get x by itself, right? Let's try factoring it. What happens when we factor it? And that's the other thing. Don't forget, even though there's no x squared. So for example, if I gave you this, how would you solve it? What would you do? Don't tell me quadratic formula. What would you do? Subtract 12, and then what? You still can't get x by itself, right? But we had a procedure for solving higher powered equations, right? Didn't you factor it? And then what were the answers? -3 and -4. You said each factor equal to 0. Same idea here when you get something like this. Take out an x. Take out an x. Remember, the zero product property. Whew, pulled that one. You don't remember zero product property. Zero product property stated you got two factors equal to 0. As long as one of them equals 0, the whole thing equals 0, right? So what do? You set each product equal to 0. And you say, oh, here you go. X equals 0. And now, I already got x equals 0. For the other side, 1 plus 2 ln x equals 0. Now I can solve for x because I only have one x in the problem. So what would you do? Subtract the 1 from both sides. Divide by 2. Don't remember your logs very well. How do we solve an ln? ln has base what? E. So how do I rewrite this using E? There's two different ways to think of it. You can rewrite it using E or take E and raise it to each of those powers. Remember? Do you remember doing this? One of two ways to do it. One way is since ln has a base E, I'm going to write the base in there so you see it. How do you rewrite logs? Do you remember this little thing? It means the E to the -1/2 equals X. That's how you rewrite a log. E to the -1/2. Oh, there we are. X equals E to the -1/2. The other thing you can always do when you're doing an equation with ln, if you recall from pre-calc, is say, oh, I'm going to do this. I'm going to take E to the ln of X equals E. Do you remember doing this at all? Remember doing this? What you do to one side of the equation, you just do to the other side of the equation. What's E to ln X? E and the ln cancel each other out. You get just X. Either way, they work. You are going to start to get into equations that involve logs. So you got to remember some of these little ways to solve them. All right. So what do we get? we get x is at 0. So when does the derivative equal 0? When x is 0 and when x equals 1 over the square root of e. Okay. All right, so remember what our original function was, y equals x squared times ln x. Because we're not done. A min-max value is not the x value, it's the what? It's the y value. So you got to take your two places where you think there could be a min or max, and then you need to plug it back into your function. So let's try 0. What happens when we try to plug 0 back into the function? Well, you have a lot of issues here. Can you take the natural log of 0? Think of your natural log graph. Does it exist? Can you take the natural log of 0? Remember, you should have that natural log graph memorized. It looks like that. Can you take the natural log of 0? No. So, yeah, forget that one. Okay, it's not even in the domain. But can you, yeah, you can do this. So what do we have for x? So we have 1 over square root of e squared ln. Well, let's leave it as this first. Let's do this. It's e to the negative 1/2 squared ln e to the negative 1. This is a lot of pre-calc review, but I told you throughout this course this is our time where we're going to spend a little pre-calc review with logarithms. All right, e to the negative 1/2 times 2 is just e to the negative 1, correct? Are we good with that part? Right, negative 1/2 times 2 is just negative 1. We good? How do we work with logs? Easiest way. Do you remember how to get rid of a power of a log? Property of log says that, yeah, ln of e to the negative 1/2 is equal to negative 1/2 ln of e. That was just one of your log properties. The power can go out front as multiplication. So then I have, by doing that, I can move the negative 1/2 out front. And then I'm left with ln of e. Come on. What's ln of e? You can always plug that into your calculator to get that if you need to. Because remember, it's e to what power equals e. That's what a log is. It means base e down here to what power is going to give you e. It has to be 1. So that just becomes 1. So what's our answer? Oh, we have negative 1 over 2e. Done. So this graph actually kind of goes like this. And there is your local or absolute min. And the absolute min is negative 1 over 2e at 1 over square root of e. So part of this problem was to review some basics with natural logs. All right. So let's write some steps down. Let's take a look at locating our extreme values on closed intervals. Just a couple steps for you. How do we locate? Because that's what you're going to do in your lab. On a closed interval. So remember, when we talk about a closed interval, it was this thing, right? That's what I mean by a closed interval. We're not talking about an entire domain of negative infinity to infinity. We're talking about some closed interval, A to B. All right, so number one. Okay, you got to get those critical points. You got to find where your derivative is either equal to 0 or does not exist. Okay, but just because you know what a critical point is. This means where does f prime of c equal 0 or f prime of c does not exist. These points are candidates for max and mins. Okay. Find your f of c's. Evaluate f at those critical points. You got to figure out what f's doing. So once you find the critical points, plug them back into the function. Just plug them back into f. Because it's a closed interval, you also need to evaluate f at the endpoints of that interval. So let's suppose my closed interval is AB. You need to evaluate f at A and B, meaning you need to find because it's a closed interval, those endpoints could be your local extreme. You don't know. You don't know until you find all the y values and see which one's higher, which one's lower. Okay, then obviously, if we're locating extreme values, that means it's the absolute max and min. Choose the largest. And the smallest for the min. So let's look at an example. I think we'll only do 4.1 today because I forgot how long and lengthy 4.1 is, where the other one is kind of short. We'll do that one on Tuesday with the graphs. And there's plenty of lab problems just for 4.1. So let's look at one example. I'm not going to give you a log this time. Don't worry. I'll give you a nice, easy one. But you got to start being able to work with those log functions. And I think hopefully you reviewed a lot with logarithms in that last example. Some like common things. All right, so let's do f of x equals x to the 4th. Now we're talking closed interval, so I have to give you the interval. All right, we got to figure out what the critical points are. So how are we going to do that? To get critical points, remember, you're looking at where the derivative equals 0 or is undefined. To figure that out, what do you need first? but set what equal to 0? Not the equation, what do we got to find real quick? Derivative of the equation. Yeah, so we need f prime. Told you I gave you a nice easy one, right? We all know f prime. You're like, oh yeah, I can take derivatives of these. These are easy. So what is it? 4x cubed minus 6. Good. Go ahead now and set it equal to 0. I am going to factor. Yeah. So does that leave me 2x minus 3? Set each factor equal to 0. So I have x equaling I believe that would be 3/2 for the other one, correct? So I want to talk for one quick minute while we're doing this problem, because this will help you with also with Tuesday's lesson. We know at x equaling 0, my derivative is my derivative is 0, so that means I have a tangent that's a horizontal line, correct? Remember what I said. What you are not confident of yet is it is causing an absolute max or min, right? Because remember, when f prime of something equals 0, you have a couple things occurring. It could be, oh yeah, it could be a max, right? It could be a min, or it could be that crazy, this thing, right? How can you be sure it's a max or a min and not a point of inflection? So think about it for a minute. What is my slope doing prior? I'll use my red pen on here. What is my slope doing as I approach the maximum? It's increasing. It's positive. Everybody see that? What's my slope doing after I reach a maximum? Always, 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 always. That's how a maximum is defined. The slope's going to increase, and then the slope's going to decrease. That must occur on a maximum. What happens on a minimum? Yeah, it decreases prior, right? And then it does what? Increase. What happens on a point of inflection? Or you could actually have a point of inflection that does that, in which case it's doing what? Okay. So if you're ever not sure that your point is a max or min, what you need to do is think about, okay, go to, just look at this right here. This is real quick. Watch. Well, at x equaling 0, my slope goes to 0. But what's happening at -1? If I real quick, and you don't need to do the work, watch, you're going to get really, really used to just plugging in numbers to find out if that derivative is negative or positive. So if I plug in -1, do it with me in your head, that becomes positive, right? If I put -1 over here, ooh, that's going to be negative. That's going to be negative. What's a negative times a positive? It's negative. What happens at right after 0? Let's use 1. I get a positive. Oh, I'm still getting a negative. Do you see that? Let's see what happens with 3/2. 3/2 is a little tricky, but 3/2 is 1.5, correct? So now let's use 1. We know that 1 leading up to 3/2 is going to cause us a negative slope, right? We already figured that one out. What if we jump to 2, which would be right after 1.5, right? Positive, positive. So we go negative, positive. So this one yields a max or min. This one does not. That's how you figure it out. Unfortunately, that's the kind of things you need to use as you start graphing functions. You got to really examine it. And you can examine it quickly that way by just thinking of, hey, is my slope increasing? Over here, my slope was decreasing and it continued to decrease. Do you see that? So you got to be careful there. So that means this is not a possibility for a max or min, but that 3/2 is. All right. They're the things you need to think through as you're doing these problems. All right, so we have 3/2. And don't forget, because it's a closed interval, our other possibilities are the endpoints. So our only possibilities for our max and min are right here. We couldn't use 0. Okay. And how do you find it at this point? Plug it back into the original equation and see which is higher, which is lower. That's it. That's all you need to do. You plug it back into the original equation. So somebody do the math for me. You all got calculators. What is original equation? Calculate what f of 3/2 is for me. Thank you. You got negative 27 over 16. Cool. All right, let's get negative 2. That's positive 16, right? Third 2. What's this plugged in? It's negative 8. 16 and 16, 32, right? I think you get 32. And do positive 2. So that's 16, 0. That one's 0. All right, what's my max? My extreme, my absolute max is 32 at x equaling negative 2. And what is my absolute minimum? Negative 27 over 16 at x equals 3/2. But you had to know to knock out that other one. So, should we plug it into Desmos real quick and see what the graph? Because here's what's great about doing these problems when you're done. Just put it in Desmos. How many of you have your computers? Go ahead and stick it in Desmos. I'll do it here, and then we'll be done. So let me plug this into Desmos. I have to get out of tablet mode for a second because I did not have Desmos open. All right, let me get in there. Always great. You're going to use Desmos a lot. So if you have one of these smartphones, get the app. Really helpful. So it was x to the 4th minus 2. Oops. Always screw something up. 2x cubed. There it is. Doesn't it make sense? Here it is. Now we had a closed interval. What was our closed interval? You can do that on Desmos. I'm not remembering right this second though, of course. You can actually, I think you put the brackets, right? Do you put on or do you put the semicolon, is it? What do you put? I forget. Anyway, we know it goes from -2 to 2. So just, I can't write on that. I can come over here. We know we're only looking at -2 to 2. But do you see at 0, even though it came out with a horizontal, it is not a max or min. That's what I kind of wanted you to see. 0 does not cause a max or min. That minimum of -27/16 occurred at 3/2. Okay? It occurred there. And the max, yeah, occurred over at -2, I believe, right? That's what we got, and that's what we got. So always check your work by looking at Desmos when you're done. Okay? Enough for today. Okay, so let me go back for a second. Hold on. So that at this point in the lessons can get you through numbers 1 through 4 in the lab.